Okay, but we are live. So thank you for attending our February meeting of the North Jersey Astronomical Group. Remember that we meet, at least are meeting online at this point on the second Wednesday of the month, and we try to have an interesting presentation for every meeting, and so that's what we're going to start out with. And then at the end of the presentation, members, please do stick around. We do have some business to talk about, well, business meeting at the end there, so stick around for that at the end. But let's proceed with our presentation here. We're going to introduce our speaker, and we're going to participate in this presentation during the program. If you have any questions, you can use the chat to ask any questions, and you can stop Jeremy and ask him those questions. So let's proceed. I'm going to turn things over to Jeremy Carlo, and he's going to introduce himself. And tonight he's going to be talking all about the wacky world of quantum physics. And so, Jeremy, if you want to take it away.
All right, thanks, Kevin, and thanks, Mary Lou, for the invite, and glad to be here. So I'm a professor of physics at Villanova University, which is near Philadelphia, but I go way back in the New Jersey astronomy community. So I've been a member of AAI since about the early 1990s. So I've been active in a couple of clubs in New Jersey. I was in NJAG for a while and STAR for a short while. Then I lived up in Canada for a couple of years, and now I'm down in Philly. So anyway, I'll maybe get started with the presentation here. Let's, you got to enable my screen sharing. All right, there we go. Let's make sure I got the correct one. I think that's it. All right, there we go. Except that now you're looking at, are you seeing the full screen or are you seeing the partial? Kevin, you're muted.
We're seeing presenter view.
Yeah, we're seeing presenter view. So
let me see what I can do here. I got to get the correct one.
I think you got to select the right window there.
Yeah, maybe that's it. No, that's not it. Seems like they're all doing the same thing.
There you go. That was it.
That was it. Okay. That one?
Did have it there.
That's the right one?
No.
Okay, that was the same one I just selected. All right, I'll do the other one. Yes or no?
No.
No.
All right, then I'll do the other one again.
That's it right there.
There it is.
All right, that's the good one. All right. So here we go. So to get us started, let's talk a little bit about classical physics. So what I have here is a couple of demonstrations, and this might bring back some nightmares from introductory physics. We have Newton's cradle, a little electric circuit, inclined plane, and of course here is the life-saving Atwood's machine. So I always explain this to my pre-med students. I call it the life-saving Atwood's machine, and they say, how does that save lives? I say, because it keeps the kids who can't cut it out of med school. Well, they're not too entertained by that, but that's that. But what all of these things have in common are two things. Number one is they're all sort of human scale objects. They're all sort of centimeters to meters, seconds to minutes, grams to kilograms. They're sort of sizes that we can deal with on an everyday basis. And they're all systems that I can kind of take apart. They have a finite number of elements, so I could take these apart and basically put it out onto a table, look at each of the parts and try to understand them, and then put them together and see what happens. And that's why these things were tackled by classical physicists, because they were accessible. Now, modern physics, on the other hand, increasingly pushes at what have been called the three infinities. So the first of these is probably the one that's of most interest to us as astronomers. That's the infinitely large, right? That's the province of astronomers and cosmologists. What are the laws of physics on the largest scales? How is the universe structured on the largest scales? Now, in parallel to that, a different group of physicists, the particle physicists, we're working on the infinitely small scales. And I put infinite in quotes because nothing is really infinite. It's just really, really big or really, really small. So at really small scales, we're talking about atomic and subatomic scales, there's a completely different set of physics which governs what happens at those scales. And it turns out it's really, really, really weird. And then there's what I call the infinitely complex, which is what you get if you take these simple laws of physics and you apply them to large systems. So any macroscopic system, like a human being, has, Avogadro's number sort of atoms, so 10 to the 23 atoms or more than that. And each of these things are interacting with each other. And even if the interactions themselves are simple, they give rise to these complex things. You can have complex chemistry. There's an entire science devoted to just atoms interacting with each other, making solids. Then you can have really, really complicated molecules that can replicate. And that brings us into biology. Then you can look at biological organisms. You can look at animals. You can look at plants. You can look at humans. How does the human mind work? Now, of course, this is all predicated on the usual hubris of a physicist, which is that all science is basically applied physics. Right? Chemistry is applied physics and biology is applied physics. So yeah, I'm kind of starting from that hill here. But essentially, modern physics and by extension, all science really pushes at these infinities, the infinitely large, the infinitely small, and the infinitely complex. Now, basically where this talk came from was last year I gave a presentation to AAI, and I talked about the infinitely large. I talked about the Big Bang and cosmology and our understanding of gravity at the largest scales. And then I was talking to Mary Lou, and we came up with the idea of maybe talking about the second one of these, what happens at infinitely small scales. So maybe not quite as relevant to astronomy, but there's a lot of physics there, and there's a lot of really interesting stuff. So I'll kind of start by presenting where we are, and this I'll call the standard model of physics. So on large scales, the universe is governed by gravity. It's the most dominant force on the largest scales, and our best current understanding of gravity is the theory of general relativity. Now, one of the consequences of relativity is that space-time must be expanding or contracting, and that leads us to the idea of the Big Bang. If the universe is expanding, it was once much smaller. And if it was once much smaller, then you can extrapolate that all the way back to the beginning. And now if you take all of that and you take a lot of the evidence that's been collected since then about how rapidly the universe is expanding and what are the constituents of the universe, how much mass density does it have, what types of matter are there, you come up with, I guess, the $3 term for this, if you want to sound fancy. It's called the lambda CDM model, where each of these letters represents something, where this lambda represents that dark energy, that's the accelerating expansion of the universe. And this CDM is something called cold dark matter. It's cold, meaning that it clumps together. It doesn't expand and fill out into space. And because it's clumpy, it tends to clump regular matter around it. And this is really how we get the first galaxies and the first stars starting to form. Right? And then in parentheses, I put this thing called inflation, which is this hypothetical period in the very early universe where the universe expanded exceedingly rapidly. We don't have direct evidence that that happened, but it would solve an awful lot of problems. And there are people looking for evidence of inflation right now. And maybe like in the next 5 to 10 years, we'll know one way or the other whether it happened or not. So that's essentially our standard model of the large scale universe. Some things that are still being filled out, but there's sort of a pretty good framework. Now, in parallel to that, on the small scale, a different group of physicists, the particle physicists, we're trying to understand how nature is organized at the smallest levels. And it turns out that our understanding of physics at small scales is dominated by something called quantum mechanics. And I'll call that the wacky subatomic world, all the crazy things that happen in the universe at small scales. And in fact, at the smallest scales, we have something called quantum field theory. And quantum field theory tells us that there are, in fact, 4 fundamental forces. It's a fun game to play that any physical phenomenon that you can think of is one of these 4 forces, whether it's magnetism, electricity, gravity, radioactive decay, friction forces, tension forces, what makes the sun shine. All of this is due to just these 4 forces. And these forces act on what I call the particle zoo. It's a certain set of particles, and these behave according to the laws of quantum mechanics. And it turns out there's some really, really weird stuff that happens there. And that's really what I'm going to talk about tonight. As far as the complex goes, I would say of the three of these, that is by far the hardest problem to tackle. I would say the very large and the very small, physicists have really spent most of the 20th century getting a pretty good handle on those and developing a good understanding for how those work. It's really just now that we're starting to tackle the really complex problems. So understanding the workings of the human brain, modeling weather, modeling climate, things like this get really, really hard. And even if we know the underlying laws of physics, how do they behave on these really, really complex systems? So there really is no fundamental theory of the complex because there are so many different things. But the way that I summarized it is I said, how do all these laws of physics, as simplistic as they are, and acting repeatedly on electrons and protons and what have you, how do they make the universe an interesting place to live? Right? If it was just a bunch of electrons banging into each other, that gets boring pretty fast. But we live in an interesting world. All right. So a couple of background points here. Just about everything that I'm going to describe is real. And when I say real, I mean that it's been observed in an experiment, that you can go into the lab, you can do an experiment, and the results of the experiment depend on something being true or false, or correct or incorrect. There's a couple of things that haven't been done. They're more like thought experiments or more extreme conditions that we've never been able to simulate. And if it's one of those things, I'll put a star, kind of as a little warning, just saying that this is theoretical speculation. But everything I'm going to talk about, crazy stuff, particles in two places at once, things like that, this is all real. This is all experimental. You can go into the lab and you can measure this. This is like everyday stuff for quantum physics. So a little idea here. This is something that I just made up, so don't use this anyplace else. No one will know what it means. I call it Carlo's razor. And it says that nature is under no obligation to satisfy our expectations. Electrons have been around way longer than we have. So if you look at that and say, no, electrons can't do that, the electron says, I've been here longer than you. I act the way that I want, whether or not you think it's right. So all we can really do is look at the experimental results. And if the experiments don't satisfy our intuition, then it's our intuition that has to take a back seat because the data tells us what's real. All right, so here's how it goes. Again, if you have any questions, maybe put them in the chat. I'm not sure if I'll be able to see them right away, but yeah, if there's any questions, just let me know. So on the smallest scales, nature is really, really weird. We have these things like wave-particle duality, the uncertainty principle, particles that can be in two places at once. There's this Schrodinger's cat experiment, which has the little scare star next to it. This has never been done, so don't worry about it. Never been done, never will be done either. So here's where we're going to start. This is called the double slit experiment. It was first done in the early 1800s. Now, if you've made any telescopes, you're probably familiar with a lot of this. The idea is I shine a light at a pair of slits. Now, in order for this to work, the slits have to be very close together. So this diagram is a little bit inaccurate. But what happens when I shine light at a pair of slits is I get this interference pattern of these on, off, on, off, on, off. These things that go kind of this periodic pattern. In fact, I can do a little demonstration of this. I hate to pause my screen share because let me do this. Is there a way to pause it? No, I'll have to stop it. I'll do a little demonstration. So what I have here is a laser. I'm shining it against the wall here. And what I've got is something here that has little slits inside of it. And when I hold that up, you see that? I get this pattern projected against the wall of these little on, off sort of things. Right? There's the laser beam. And that's the pattern that I get when it goes through this little grating here that essentially has little slits cut into it. So let's bring the screen back. I think it was that one. Is that the right one or the wrong one?
Right.
That's the right one. Okay. I have two that look identical. So, all right. So here's what happens. The result of this experiment tells us that light is a wave. And the way that we understand that is the light that comes through these two slits forms these spherical waves which are traveling outwards. And I can show you how this works in a classical wave. This is just the surface of a pond or something. And if you just go and kind of tap your finger in two places on the water, it generates these little ripples that go outwards. And then when these two ripples meet with each other, they interfere. So if I imagine putting a screen or something across there, I would see little up, down, up, down, up, down as I went across there. And in fact, that's exactly what we see here. So it's the fact that light is a wave, it has a finite wavelength associated with it, and it travels in these spherical waves. When it goes through two slits, I get this interference pattern. Now, it's kind of interesting that this is not unique to light. Instead of a beam of light, I could make a beam of electrons, and it does exactly the same thing. You get the little pattern on and off. I could do a beam of protons, I could do a beam of neutrons. Experimentally, a little more difficult to do, but you get the exact same results going through slits like that. So light is not unique. Even things that we think of as particles, like electrons and protons, in fact, have this wave nature as well. But light is also in the form of particles. And I won't talk too much about this experiment. This is something called the photoelectric effect. And basically what you show is that when light is produced or when it is absorbed, it's done so in these discrete packets, which were called quanta, or we now call them photons. And there's no such thing as half a photon. It's all or nothing. And in fact, it's correlated with color. Blue photons have more energy than red photons, and you can't get half a blue photon. It's one blue photon. And this light is emitted and absorbed in these packets, in these lumps, like particles. So in fact, light is a particle and light is a wave. It's both at the same time. Now, it's very easy to just kind of paper that over and go, okay, it's just two words. That doesn't really mean much. But these two ideas are really contradictory. Particles are local things. So I have here some billiard balls, and that's kind of what we think of when we think of particles. They're local, right? It's here. It's there. It's not anyplace else. There it is. It has a very defined shape. It has a defined size. We know exactly where it is. We know exactly how fast it's going. We know exactly how much energy it has. All of these things are very definite, and we know exactly where it is. A particle is local, but a wave is non-local. What makes this a wave is the fact that I can look at, let's say, what's happening over here and what's happening over here, and there's a correlation between those. If it's doing this in one place, then it's doing this someplace else. And there's some mathematical relationship that describes one in terms of the other. If we lose that, we don't have a wave anymore. Then, or I should say, it's no longer coherent. So coherent means that it makes sense over some length or time scale. What makes this a wave is the fact that it's coherent over large scales, typically, several times or more what the wavelength is. If I just had a really, really tiny piece of a wave, well, that's no longer a wave. If I just looked at a little piece like that, that's not a wave anymore. The physics that makes it move no longer works, right? It's like one guy at a stadium doing the wave. It just looks stupid. It's not going to work. It's just one person doing that, and there's nobody else around following. So waves, by their nature, have to be non-local. They have to be distributed through space. So these two ideas are contradictions in terms. Okay, so now what I'm going to do is I'm going to push a little bit further. So let's go back to the double slit experiment, and I'm going to block one of the slits. So I just block one of them with a big piece of duct tape or something. I block one of the slits so that only one of them is remaining. That double slit interference pattern goes away, and instead what I see is a single slit diffraction pattern. This is something that should be familiar to us as astronomers. If you go out on a night where the seeing is pretty good, I mean, not that that ever happens around the Northeast, but if you went out on a night where the seeing is pretty good and you looked at a star, you don't see a pinpoint. What you see is kind of a blob, and then there's little rings around it, the diffraction rings. And that's exactly what this is. This blob is what we call the Airy disk, and then this would be the first diffraction ring surrounding it, and then there are more outside that. So why does that happen? Well, your telescope is a single slit, right? This star is sending out light, it's bathing the entire Earth with light, and here I come out with my puny little telescope that just takes the light that goes into this area that's this big and sends that to the eyepiece. It's effectively a single slit. And because it has a finite width, I get a diffraction pattern. And in fact, these are complementary to one another. The bigger the telescope, the tighter that diffraction pattern is, which is why larger telescopes have a smaller diffraction limit. Although then again, you never really get to see that around here because usually it's the atmosphere boiling around that limits that. But if you had really good, really steady seeing, you would see that little diffraction pattern because the telescope is a single slit. But there's a difference here. So when I block one of the slits, I get the single slit diffraction pattern if both slits are open. I get the double slit interference pattern. It looks very, very different. So I can do the experiment and see which one of these I get. All right, everybody with me so far? All right, here we go. Now I'm going to flip the script. Same experiment, double slit, but now I'm going to dim the light source down until I'm only emitting one photon at a time. So I've turned the intensity down so much, or I've put filters in front of the light, that one photon comes out, does its business, gets absorbed at the other end. Then another photon comes out, does its business, gets absorbed at the other end. So only one photon at a time is going through. So now what we decided before was that when photons are going through both slits at the same time, we get the interference pattern, but if it only goes through one, we get the diffraction pattern. So in this case, which pattern do I get? Do I get the single slit diffraction pattern because it's one photon at a time, or do I get the interference pattern? Which one do I get? All right, I won't keep you in suspense. The answer is we get the interference pattern. But wait, we already agreed that we only get the interference pattern when light goes through both slits at the same time. So somehow that one photon is going through both slits. It's in two places at once. It's being emitted at one point, it's being detected at one point, because you can even do this like in an event mode, where you're not just putting a piece of film and then counting up the number at the end. You're actually saying, okay, I just detected a photon at pixel 1763. And then you send the next one and say, okay, I detected a photon at pixel 2594. You can do it literally one photon at a time in like this event mode if you have a really sensitive camera, yet you still get the interference pattern. Somehow the photon is going through both slits at once. Weird, right? Okay, one more. Back to the double slit experiment, one photon at a time. Now what I do is I put a little gate or a little detector on each slit, and all it does is it tells me when a photon went through. So if a photon goes through slit A, there's a little thing that goes off and says, okay, a photon went through slit A. Maybe it's like a little light bulb on top, or maybe it's just a little electrical pulse that goes to a computer. So now what happens is I do the experiment, one photon at a time. I have the detectors on the two slits, and I ask what sort of a pattern do I get? So now, do I continue to get the double slit pattern, or do I get the single slit pattern?
Single.
And what happens to the lights? Jeff, did you have a thought?
Not yet.
Okay, all right. Oh, I thought you were saying something.
I didn't say anything.
Okay. All right, so here goes. If I put the detectors there, every single time one light lights up, you will never see both lights light up at once. So remember this stuff about the photon going through both slits at once? That's gone. It'll go through one or it will go through the other. It will never go through both. And also the two slit interference pattern goes away. Now we just get the single slit pattern behind one slit and the single slit pattern behind the other slit. Because now basically what we have is a bunch of photons that go through slit A that produce a pattern, and a bunch of photons that go through slit B and produce their own pattern. And since it's one photon at a time, they can't interact with each other. So you get one diffraction pattern and one diffraction pattern. Or to put it another way, the very act of measuring or of observing the system changes the system. That I've actually changed it just by putting that little gate there in front of the slits. If I want to go really crazy, I could even just put a gate on one of the slits. And then it turns out that I get the same thing, that even the photons that go through the other slit are still affected, even though the other slit is, or the other detector is just sitting there like the Maytag repairman doing nothing. So even the fact that the slit says, oh, nothing happened here, still changes the system. So even the non-observation changes it. So the way that we get around this is we understand that these quantum entities, things like photons and electrons, are described by something called a wave function, which is a wave-like thing. And I showed some pictures here of what they look like. They look sort of like waves, and they describe how this photon spreads out, right? So somehow it's spreading out through space and then coming back together when it's time to be detected. So this wave function describes how that happens. But in order to do that, it has to be very, very different from a classical wave, like the thing that goes on the surface of the water. So, all right, this is a death by PowerPoint slide here. I know these are evil, so I keep them to a minimum. So the postulates of quantum mechanics say this. So number one is any system is described by this wave function. And the wave function, the symbol that they use is the Greek letter psi. It looks like a pitchfork. So this little pitchfork function here describes what this wave function is, or describes the system. This wave function evolves through space and time according to this nasty looking equation here. Again, another bad thing is putting equations. I think Stephen Hawking said that every time an equation is shown, half the audience disappears. Haven't seen anyone log off yet, but all right. What is this? Well, remember that water wave? There's an equation that describes how that water wave evolves, and it's called the wave equation. This Schrodinger equation is actually a form of the wave equation. It's a little bit different mathematically. There's a couple of little things, but it turns out that it doesn't matter all that much. It describes behavior of a wave. So something that kind of goes like that through space, it spreads out. It's a normal wave equation. All right, so number 3 tells us that anytime we do a measurement or an observation, that's described as an operator which acts on the wave function. So an operator in math is something that does something. So if I have some function or some number, I could multiply it by 2, or I could square it, or I could take 1 over that. Those are operators that are acting on it. Any measurement that I do, is there a chat comment here?
Nothing significant.
Okay. Yeah, so any measurement that I do is an operator which acts on the wave function and actually changes it. So it actually changes the system. Now, number 4, and this is where it starts to get a little bit controversial, the wave function tells us the probability of a given measurement result. Technically, it's the wave function squared that gives you the probability. But let's say if the wave function squared at some point is 0.1, that means there's a 10% chance that the particle will be there. And if the wave function is 0.3 someplace else, that means there's an 0.3 chance that we'll find it there. So that's essentially what that means. It just tells us the probability of measuring a certain thing in sort of the same way as if I roll a die, there's a 1 out of 6 chance that I would get a 5 and a 1 out of 6 chance that I would get a 2, and so on down the line. The wave function is sort of the same thing. It quantifies what those probabilities are. Now, the last point is that any measurement will have a definite result. If I ask a question, I will get an answer. If I say, where is this particle, I will get a definite answer. If I say, which slit did that photon go through, I will get an answer. So any measurement that I do will have an answer associated with it. So if I had, say, a photon described by a wave function that looks like this, and I ask, where is the photon? What's going to happen is my measurement will tell me the photon is right there. And when that happens, the wave function collapses. It's not this anymore. Now it's that. That's what the wave function looks like. It's 1 at this point right here, because I know that's where the photon is, and it's 0 every place else. So if I measured the position of that photon exactly, that's what would happen. I would collapse the wave function to that, which means that it's no longer the same system. I've changed it. It used to have that wave function. Now it has this one. Now then, of course, as soon as I turn my back, the Schrodinger equation comes back and this thing will start to spread out through space again. But then if I turn around and say, where are you now? Then it's going to collapse back into, maybe it'll be over here this time. And then as soon as I turn my back, it starts to spread out again. So that is basically how wave functions behave. So now Einstein had a big problem with this. Einstein said God does not play dice with the universe, that the universe just can't be random like that. But it turns out it is, that this is what happens when we do the experiments. These things, in fact, are random. So there's kind of an attractive idea, and I think everyone who learns quantum mechanics comes up with this idea. They say, okay, I buy the whole probability thing, but that's not really what happens. The photon is really over here. It's hiding someplace inside the wave. I just don't know where it is until I do the measurement. Right? As soon as I do the measurement, then okay, I know that it's there. And then maybe it'll move someplace else after that, but it's there. It's definitely there, and it moves around. And this is what we call a hidden variable. So the idea is that sort of reality exists at the lowest level. We're just prevented from observing it. Or at least if we try to observe it, the idea is we're looking at really small particles. So if I try to measure something, well, how do I measure something? Right? If I wanted to set up like a motion detector to let me know if a burglar came onto my property, I might set up a little laser And if the burglar walks through, he cuts off the laser for a second, and then we know that something happened. Well, what's the laser? It's a bunch of photons going across like that, which the burglar will never notice if he walks through it, but maybe a single photon going through, well, that's going to notice getting hit by photons. So you can kind of understand why the wave function would change. And then you go, well, there's a hidden variable inside there, and we just can't see it until we actually do the measurement. This is wrong, though. And the reason we know it's wrong is you can do something called the delayed choice experiment. Again, there's no asterisk here. This was actually done back in the 1980s. It was a group led by Alan Aspect in France, and he was awarded the Nobel Prize, I think, about 5 years ago. So basically what they do is they generate a pair of particles. They have like an atom or something which decays, and it produces a pair of particles. And now because of things like conservation of charge and conservation of angular momentum, these things have to, let's say, spin in opposite directions. So these things come out, you let them separate some distance, and now what you do is you measure one of the particles. But what you can do is you can decide what to measure at the last possible moment. So you wait until like a few nanoseconds before and go, okay, we're going to measure this, or we're going to measure that. And when you measure that, you collapse the wave function of that particle. Now, an instant after that, another group of scientists in another room measure the other particle, and it turns out that the choice that you make on the first particle affects the distribution of outcomes on the second experiment. And that's true even if the distance is greater than the speed of light times delta t, the difference in time between the two measurements. What that means is the wave function collapses, and it does so instantaneously everywhere, that there isn't enough time for a hidden particle to jump from one side to the other. Even if it travels at the speed of light, it can't get there fast enough to say, oh, by the way, they're measuring X. You should act like we just measured X in the other room. Or it can't go across and say, they just measured Y over there. Get ready, make it look like we measured Y. It happens so quickly that you can't explain it that way. So that brings me to Schrodinger's cat. All right, so here comes the scary star. This is an experiment that was not done and has never been done. So the idea here is you put a cat inside a box. Now you have a little box here that has some radioactive atom inside it. Now, if this radioactive atom decays, it causes a little lever to flip. And when the lever flips, this hammer falls and it hits this jar filled with poison. It breaks open the bottle and the cat dies. So now the question is, I seal up the box, I wait a while. I don't know whether the atom is decayed or not. If it hasn't decayed, the cat is alive and well. If it has decayed, the cat has died. The question, is the cat alive or is the cat dead? Now, if I open the box, I immediately know the answer. But if I don't open the box, I don't. And this is the thought experiment, right? It's just like the double slit experiment. Well, if the photon went through both slits, then the cat, in a way, is alive and dead at the same time. And until we actually do the measurement, we don't know which way it turns out. Now, the problem here is that a cat is a macroscopic object. In order for this stuff to work, you need to have a system which is coherent. That means you have that wave that goes like that. And a cat is big enough, there's enough atoms and molecules bouncing around that it becomes incoherent pretty quickly. So this is not a real experiment. The cat would essentially collapse the wave function pretty quickly of its own accord, whether or not we look into it. At least that's kind of my hard-nosed experimentalist interpretation. But of course, it's not a scientific question because there's no way that we can check. The only way I know is by opening the box. And you might say, well, I could put a stethoscope and listen to see if I can hear the cat making any noise, or I could use a little infrared gun to see whether there's any body heat coming off of the cat, but that's a measurement. That means I've looked inside the box in a way. That means that I have observed the system. Right? It's the old question about a tree falling in the woods and no one's around to hear it. Did it really fall? It's something that can't be addressed by science because science can only address what can be tested, what can be discerned by experiment.
Jeremy, we had a question related to that, and I think you partially already have answered it, but Edward asked, are you saying that when I take a measurement of a particle within a wave, it is more like a snapshot? Once taken, the wave is only then assumed to continue. Please explain what is meant by a collapsed wave. And he adds, so the cat is both alive and dead? Question mark.
Yeah. Well, we can move away from the cat. Let's talk about photons. The idea is the photon is described by this wave function, which essentially describes the probability of where you'll find it. The act of measurement changes that wave function to something else, meaning after you do the measurement, the probability that you would find it someplace else is different than the probability of finding it there before the measurement was done. I don't know if that directly answers the question, but it's not a particle in a wave, right? That's that hidden variable idea that doesn't quite work. The particle is the wave function. It actually is spread out. It's not like Waldo floating in the water there. It actually is spread out through there. So that's why I said the Waldo thing is wrong. It's kind of an attractive idea when you're learning quantum mechanics. I think every student has come up with this. Go, why can't these idiots figure that out? It's sitting right there, but it's not. It actually is everywhere.
Thank you. I think I got it. I think that maybe some of the confusion, at least on my side, was you referenced the like a pebble in a lake or on water, and isn't that wave transference just made up of water? I mean, it's really water in motion. So maybe that ripple in a lake doesn't work.
Yeah,
Is that the same analogy?
Yeah, that's a classical wave, so that's where it does break down. Right?
Okay.
So the pebble is a particle, right? That's what you would consider a classical particle, and it's generating a wave. But in fact, things like photons have aspects of both of those.
Okay. Okay. Yeah, because one of your illustrations had that.
Breaks down.
Yeah. Okay. Thanks. I think it's a lot to take in. Right. Thanks.
Yeah. Oh, wait, there's more. I think this I'll kind of skip over. There are some different interpretations of how to get around this. So everything that I've said here is kind of the standard. This is called the Copenhagen interpretations. This was Niels Bohr and others. They met in Copenhagen and tried to figure out what the hell does this stuff mean. And they came up with kind of the simplest Occam's razor picture with this idea of the wave function collapsing. But there are other ways to think about it. Some people have gone by this many worlds interpretation. And the way I like to think about that is, remember in Back to the Future when Biff took the sports almanac back to the past and he like branched off that alternate universe where Biff ran the world? It's kind of like that, except that, inside my eyeball, there's a little electron. And maybe that one electron hits another electron. And then depending on what happens there, it actually branches off two totally separate universes. So there's this universe, and there's another universe which is exactly the same, except for that one electron in my eyeball being slightly different. Well, and there's nothing special about that electron. We all have eyeballs. We all have electrons. So you just get this infinite proliferation of universes. So that's what happens with the many worlds interpretation. There's a many minds interpretation, and the idea here, and this gets into Schrodinger's cat, it's the idea that you need a conscious being to collapse the wave function. This is something that's not really subscribed to by many physicists. It kind of gets into some kind of woo-ish ideas about consciousness and what's conscious and what's not. Then there's this theory of pilot waves, which was proposed by David Bohm. And this kind of builds on that idea of the little Waldo floating around, but it has to be different in that you can't have a local particle. It has to be non-local in order to explain that delayed choice experiment. But ultimately, all four of these interpretations say exactly the same thing about experiments. Anything that I can actually measure, all four of us tell the same exact story. The only difference is what happens behind the scenes. It's what happens inside the box before I open it up, right? Do I interpret it as collapsing wave functions? Do I interpret it as new universes branching off? Do I interpret it in terms of consciousness? Or do I interpret it in terms of these pilot waves traveling through space? So most physicists basically follow the Copenhagen interpretation because it's kind of the simplest, and I think the math is the easiest to work out, and it has sort of the least overhead, the least amount of baggage. All right. So a little question here, what do atoms look like? So if you open up any science textbook, you're going to see a picture that looks like this, what we might call the solar system atom or the Bohr model of the atom, where these electrons are like little planets and they're all orbiting around. Here's Mars and here's Jupiter and here's Saturn, and they're all orbiting in their own little things. This is totally wrong. This is not what atoms look like at all. Maybe this is a bit more of an accurate picture where the electron, even in, say, something like hydrogen that only has one electron, it's sort of a cloud. It spreads out and it fills all of this space. That's the wave function of the electron. Now, of course, if I say, where is the electron? I'll get an answer. The electron will be right there. I'll get an answer. But then as soon as I turn my back, it's going to spread out and fill that cloud again. So that's kind of a more accurate picture of what an atom looks like. It's kind of this thing that's sort of seething with activity. But remember, even if it's just one electron, it forms this cloud. And we have no way of knowing where the electron is until I actually do the measurement. But it's important to say this is it's not just chaos. That electron has a very well-defined energy. It has a very well-defined angular momentum and all of these other things. And that's in fact what the Bohr model gets at, is these electrons are in fact ordered. They have very definite amounts of energy, and that's what makes spectroscopy possible, right? Why we can see spectra inside stars. Very definite energies, very definite angular momenta, but in position, they're all over the place. Their wave functions are essentially combobulated all over the place in position. So now there's something called the uncertainty principle. So wave functions are squishy things. So you may have heard something about the uncertainty principle, saying that it's a limit on how accurately we can measure particles. And you might say, well, that's just stupid scientists. They just need better detectors. They just need to be more careful when they do measurements. But it's actually not that. It's actually the nature of these particles, which you can think of as not like billiard balls. They're sort of more like squishy, like water balloons. If I took a water balloon and I tried to squish it in one direction, it would expand in the other direction because it has a fixed volume. And it turns out that when I measure things, sometimes they're complementary, because when I measure something, it collapses the wave function, but it may collapse it in a way that affects another measurement. So for example, velocity and position, technically momentum, but velocity is sort of the same thing. These are complementary. So if I say measured the position of a particle, that affects measurements of the velocity. So if I measure the position really, really accurately, I can't measure the velocity very accurately anymore because I've spread that particle out. Or if I measure the velocity very accurately, I've spread out its position. Right, so there's this joke about Heisenberg is in a car and then a cop pulls him over, says, I'm going to tell you exactly how fast you are going. And Heisenberg says, thanks, now I have no idea where I am. Because once you know your speed, you no longer know your position. Or I could try to meet somewhere in the middle where I sort of know the position with some uncertainty, and I know the speed with some uncertainty as well. So, little astronomy here. One of the consequences of this is if I take something like the sun and I compress it down, what I'm doing is I'm taking all those electrons and I'm confining them to smaller and smaller spaces. Well, if I take those electrons and I squish them down in space, that's going to expand them out in velocity, which means they're going to have more energy. And this is what prevents white dwarfs from collapsing. Gravity is tending to make them collapse, but the more I try to squeeze it, the more energetic those electrons become. It's sort of like putting an animal into a cage. Like if you've ever put a dog into a kennel, the smaller that kennel is, the harder that dog is going to fight. Right? Those feet come out like that and he doesn't want to go in there. And when you put him in there, he's running around and going crazy. The smaller that is, the more that happens. Sort of the same idea here. If I try to confine these particles, it increases their average energy, or the spacing between energy levels. And that's why white dwarfs are stable against collapse, up to a certain limit. Eventually gravity wins and then they collapse further, and then you end up with neutron stars. Same idea here, except that now it's neutrons pushing back, and neutrons are 2,000 times heavier, so they push a lot harder. And that's what prevents neutron stars from collapsing. Another consequence of this, energy and time are another set of these complementary variables. So I can measure time very accurately. So I can say when exactly something happens, but then I don't know how much energy it has. Or I could measure the energy of something, but then I don't know exactly when I measured the energy. Here's why that matters. Conservation of energy is fuzzy. So all that stuff we learned about in classical physics, energy before equals energy after, on small scales is actually kind of fuzzy. It's sort of like a credit card, right? You can spend more than you have for a while, because eventually the bank comes looking. And that's kind of what happens. So conservation of energy is enforced on long time scales, but for very short amounts of time, you can escape from that. And the biggest consequence of this is that you can actually have little particle-antiparticle pairs that pop out of the vacuum spontaneously. They suddenly appear and then they annihilate again, a tiny fraction of a second later. So if you just look out into your empty room, imagine sucking all the air out of the room, it would be a perfect vacuum. It's actually not a vacuum. It's actually little particle-antiparticle pairs popping into and out of existence constantly, all the time. Notice that I didn't put the star there saying that that's speculation. This is actually measured. These are called virtual particles or vacuum fluctuations, and we know that these exist. There's something called the Casimir Effect. Take two metal plates, put them close together, and there's actually an attractive force between them. Okay, I know. Maybe they have electric charge, so maybe there's an electrostatic force. Maybe there's radiation pressure. Maybe they attract each other gravitationally. Maybe there's a magnetic force. There's all this other stuff. Well, you can calculate what those are, and you can subtract those off, and there's still an extra force that's left over after all of that. And what is it coming from? It's coming from those particle-antiparticle pairs, which remember I drew as like the little billiard balls on the last slide, but we know that they're really those fuzzy wave function things. They're actually buffeting the outside of these plates from both sides, but the area between the plates, since they're so close together, you don't get those particles because the space is too small. They're excluded. You see something very similar on a classical level. I don't know if you've ever seen this if you have boats out on the water. If you have a boat sitting there on its own, it's getting hit by waves from the left, it gets hit by waves from the right. On average, it equals out and the boat kind of sits there. But if you have two boats side by side, one boat is getting hit from the outside, the other boat is getting hit from the outside by waves, but the space between the boats, there isn't really any waves there because the boats themselves exclude it. So those boats will tend to move closer together over time. This is the same sort of idea. These plates attract one another. This is kind of an interesting experiment to do, but in fact, there's much more readily observable things. Atomic spectra have a small shift. It's called the Lamb shift. It's due to the same thing. There's something called vacuum screening of the electron's charge. So if I measure the charge of an electron and then I go really, really close, I find the electron's charge is actually bigger by something like 1%. Actually, it's a little more than that. It's somewhat bigger. And that's because when I'm at a distance, I'm not just seeing the electron, I'm seeing the electron and then all of those virtual particles around it, which tend to partially screen out the charge of the electron. So these have experimentally verifiable consequences, these little particles popping into and out of existence. Kind of an interesting one here. This is my second scare star for the talk. Something that theoretically exists but has never been observed. If you have a particle-antiparticle pair produced right near the event horizon of a black hole, if one of them falls inside, it can't escape. And the other one ends up on the outside. And if this positive charge ends up escaping, well, after a little while, the universe looks and says, hey, wait a minute. Before there was a black hole. Now there's a black hole and there's a positive charge flying away. Where did the energy come from? And it had to come from the black hole, right? Because it gets left standing there holding the bag, if you will. The black hole loses mass. So in fact, this is a mechanism by which black holes can lose mass, right? Normally they just gobble up more and more stuff. So there's only one thing a black hole does, and that's grow. But this is a mechanism by which black holes could actually lose mass. But nobody's observed it yet. Because black holes are far away, thankfully. I don't think we want one in our neighborhood. But maybe if we had one nearby, we would be able to observe this. So kind of an interesting consequence. All right, so you take all these ideas about particles popping into and out of existence, and this leads to something called quantum field theory, which is essentially our most comprehensive understanding of what happens at subatomic scales. And you might ask, why is there something rather than nothing? And the answer is that there is no nothing. Even what we think of as nothing is actually these little virtual particles popping into and out of existence, and we call those quantum fields. It's kind of like a fish in water. Right? The fish doesn't know about the water since it's always been surrounded by water, yet there it is. And the water does have effects, right? There could be a current in the water and that will push the fish in one direction, right? Whether or not it's aware of the water, it feels the effects of it. And we feel the effects of these quantum fields through the Casimir effect and the Lamb shift and things like that. And what it also says is what we think of as forces, things like electrostatic repulsion and attraction, gravitational forces, magnetic forces. What they actually are is these are mediated by particles throwing little virtual particles back and forth between each other. So in fact, two electrons traveling through space throw photons back and forth, and that tells them repel from each other. Because there is this problem in physics, the idea of action at a distance. So right now I'm talking to you, and the reason you can hear me is there's an unbroken chain of stuff, right? The air comes out of my mouth. There are sound waves which come towards the microphone on my computer. It gets converted to electrical signals. The electrical signals go someplace. They probably get converted into light through a fiber system. Then there's a interstate fiber that runs to someplace in New Jersey. It gets converted back to electrical signals, ends up at your computer, and then your computer converts that back into sound waves, and the sound waves travel through the air and reach your ears. There's a continuous unbroken chain all the way through. If anything in there breaks, all of a sudden you don't hear me anymore. So this idea of action at a distance is a big problem in physics, and this gets around that problem by saying that what's happening here is these two particles, which are separated by what we think of as empty space, are actually interacting with each other, and they interact by throwing these virtual particles back and forth. So Feynman was quite a character. Feynman was the guy who came up with these diagrams. They're now called Feynman Diagrams. So he had this big van, and he painted some Feynman diagrams on it, and he was driving around Caltech where he worked, and somebody stopped him and said, "Hey, why do you have Feynman diagrams on your van?" And he said, "Because I'm Feynman." So it's, yeah, I think his license plate on that was Quantum, but I think Quantum was too long, so he had to leave out the U. So it was Quantum. So it was a famous van. In fact, I think it still exists. Somebody has that van, and they're driving it around. So yeah, before you get too lulled into complacency, this is what Feynman diagrams actually represent. They're just awful equations. And essentially what these describe is the probability of a certain interaction to occur, right? This describes the strength of the repulsion of two electrons in this case. I think this is a scattering reaction. So you have one particle and another particle coming close and then repelling from each other. What you can do is by solving this diagram, and each of these little vertices corresponds to some nasty integral that looks something like that, you can actually solve for the force between these two particles. So we can do experiments in places like the Large Hadron Collider. Here's a nice little picture of some particles. This is something called a cloud chamber. So the idea here is the particles come in and we apply a magnetic field which causes them to curve around in circular paths, and that tells us the mass and the velocity of those particles. So by doing this, we can sort out which particles are positively charged and negatively charged, how fast they're moving. Like something you see here, it looks like a neutral particle comes in and then just suddenly splits off into two charged particles. So you see that there? So neutral particles don't generate paths because they don't ionize the trail going through here. So that just split off and it produced a positively and negatively charged particle. And because the paths are almost straight, we know that they're very, very energetic. Slower moving particles go in these spirals, and in fact, they spiral inwards. Here's an interesting one that kind of spirals around and then it just disappears. Probably got absorbed by it, right? It probably started here and then got absorbed over there with lower energy. So it just got absorbed by an atom, probably an electron or something, and it just got caught up by one of the atoms. So you can do a lot of fun stuff. And it turns out that there's a relatively small number of elementary particles. So in fact, protons and neutrons are made out of what are known as quarks. These have some interesting names, up, down, the charm quark, the strange quark, the top quark, and the bottom quark. Came up with interesting names because I guess they could call it like the A123 or the Psi 457 or something like that, but they decided to give them interesting names. Right, there's our friend the electron. We've got the neutrino over here. There's actually 3 different types. And then, there's different generations of these particles that are basically heavier and shorter lived for the most part. But in fact, almost everything that we deal with in nature, right? All the elements of the periodic table, normal matter, everything we find on the Earth is in fact these 3 particles, the up and the down quark and the electron. That's it. So these are called fermions. These are what we would call the matter particles. And then on the other side, we have what are called the bosons. These are the particles that are the mediators. They're the ones that go back and forth to exchange these forces. There's the photon, our good old friend. And then you notice there's a couple other bosons, and these are responsible for the other forces. And there's also the Higgs boson, which is what gives particles their mass. So it's somewhat surprising that everything that we see, all the elements in the periodic table, all the complex phases of matter, all the materials that we make, in fact, are made up of different combinations of just 3 particles. And then there's other ones which we basically make in particle accelerators, and they decay within microseconds or less. So we really don't see those. So there's a lot of questions about why are these even necessary for the universe? And it turns out that they are important, that it actually is important to have these generations of particles in order to get an asymmetry between matter and antimatter. And that's obviously why we're here, because there is an asymmetry between matter and antimatter. At some point early in the universe, there was more matter than antimatter, and that's why we matter. Because otherwise we would just be photons, because matter and antimatter would annihilate. So these higher generations actually are important. You know, despite the fact that they're so esoteric, they were really needed in the early universe in order for there to be interesting stuff. Now, even more surprising than that is that every interaction in nature can be described by one of 4 forces. So there's electromagnetism, which combines electric forces and magnetic forces. There are these 2 things called the strong and the weak nuclear force. One of them is strong and one of them is weak. That's why they got that name. What they have in common is they're very, very short range. So they basically only affect scales within the atomic nucleus. So unless you're talking about things like radioactive decay, you don't see these in everyday life. And then you have gravity. So basically everything other than radioactive decay is either electromagnetism or gravity, and that means that everything other than gravity is electromagnetism. So friction forces, tension forces, electric forces, light, radio waves, what else? The force that keeps me from falling through the floor is an electromagnetic force. Why don't I fall through the floor? Well, there's electrons in my butt and there's electrons in the chair. They're both negatively charged, so when they come into contact, they repel. It's just standard like charges repel. That's what keeps me from falling through the floor. And that's convenient because I'm on the 8th floor right now. It's a long way down. So that's where gravity would win. Now, the interesting thing is gravity is way, way weaker than the other forces. So in fact, it's even weaker than the weak force. The weak force is 30 orders of magnitude stronger than gravity. It's the weakest force. So in fact, another Feynman story was Feynman was basically saying this, and he said, you know, the problem with gravity is it is too damn weak, and he pounds on the table, and then this big giant speaker, you know, bolted to the roof of the lecture hall just falls down and crashes onto the floor, boom, and everybody starts laughing. So gravity is really, really weak, but for some reason it dominates at large scales. It wins out, and the reason is that gravity always adds. With electromagnetism, unlike charges attract, so if I stick a bunch of positive charges someplace, they're going to glom negative charges onto them, and that's going to neutralize it. So the electromagnetic force essentially gets killed off to a large extent. But gravity adds. If I put a big mass someplace, I pile more mass onto it, it just gets more and more gravity. It gets stronger and stronger. So on the largest scales, gravity wins. It reigns supreme. But on the smallest scales, gravity is basically non-existent. It's just so much weaker that it's impossible to measure. Like if I wanted to measure the gravitational force between 2 protons, it is orders of magnitude smaller than anything I could measure with any equipment that exists today. So that makes it really hard to do the experiments. And also, mathematically, gravity is very different. So those 3 forces really behave very well when it comes to these quantum field theories. So describing particles getting thrown back and forth, and that's how we get the repulsion and all of that, it works really well. But explaining gravity that way is really, really difficult. So what's kind of cool is you can write down the standard model of particle physics in one big equation. This basically describes energy. There's a term that represents kinetic energy. There's a term that represents electromagnetism. There's a term that represents the strong force, a term for the weak force, and there's a term for the Higgs boson, which is mass. Gravity is not in here because nobody has figured out how to make a term that fits gravity. Nobody's figured out the mathematical model for it. And of course, even if you did, the experiments are too damn difficult to do. So the idea of unifying all of these forces is what's called grand unification. So, you know, historically, things like electricity and magnetism and light were combined into electromagnetism. Well, it turns out electromagnetism, the weak force, can be joined together fairly easily. The strong force appears to fit in with that as well. And in fact, at really high energies, the conditions in the early universe, those 3 forces are actually indistinguishable. It's only when everything cooled down that you could start to see the differences between them. And now the big question is whether you can fit gravity into that model. And there are all of these ideas, things like supersymmetry, string theory, quantum gravity, where they've tried to explain this, but the math gets really, really complicated, and the experimental testing is even more complicated. So here we are at the end. So physics at really small scales is very, very weird. You have wave-particle duality, particles in two places at a time, wave functions that collapse, the universe being run by probability and uncertainty, virtual particles popping into and out of existence. And of course, every phenomenon that we know of is due to 4 possible forces. And in fact, the vast majority of them are one: electromagnetism. Now, as astronomers, I think we're probably more concerned with physics at large scale. So if you tuned in here late, you're probably wondering, what is this guy talking about in an astronomy club? Why should we be interested in that stuff? Well, large scales are interesting too. You have things like time dilation and black holes. But if we go back to the really early universe, the very large becomes the very small. So in fact, getting all that together, and really the very large scales and the very small scales, the laws of physics have very, very different flavors. Relativity is written like in a totally different language from quantum mechanics. How do we get those to play together? It's like relativity is like written in Sanskrit and quantum mechanics is written in Latin. How do you merge these two things together when you have people working in these fields don't even speak the same language? That relativity is about space-time being curved. It's a classical theory, whereas quantum mechanics has these wave functions and collapsing functions and probabilities and particles in two places at once. Totally different languages. How do you get these to fit together? And we're going to need to do that if we're going to understand what happened in the very early universe. And I think that's a pretty good place to stop. And thank you for your attention. And I look forward to any questions.
Hey, great. Speaking of black holes, Jeff had a question. What is the difference between a neutron star and a black hole in terms of quantum physics?
So let's see. So a neutron star has not collapsed to the point that light can no longer escape. It's actually almost there. If a neutron star went a little bit further inward, it would turn into a black hole. So a neutron star it's a macroscopic quantum mechanical object, is an interesting way to put it.
Right.
Because you have these neutrons and the fundamental interactions between them are quantum mechanical in nature. These things, they rotate very rapidly. So they are quantum mechanical monsters, if you will, but they're also relativistic monsters because you have very, very strong gravitational fields, a very, very strong time dilation. Now, if you go a little further, you go all the way to a black hole. Now, the defining characteristic of a black hole is that event horizon, right? It's the distance to which you go, and if you cross that event horizon, there's no coming out because the escape velocity is greater than the speed of light. Now, what exists inside the black hole? Nobody knows. According to general relativity, there's what's called a singularity at the center. So all of the mass collapses to a single point at the center. But that's something that doesn't make sense in quantum mechanics. In quantum mechanics, you don't have single point masses like that. You have wave functions and you have uncertainties. So what actually is at the center of the black hole? Nobody knows. And that's really where you need to merge quantum mechanics with general relativity in order to understand that. So we have a pretty good handle on what happens at the event horizon, because that is understood in terms of general relativity. But what happens inside the black hole, nobody knows. You could go there to find out for yourself, but it will be a very quick trip. It will end with you dying, and there's no way for you to come back. Well,
No way to tell about it.
no known way to come back.
Right. Okay. Circling back to an idea that you were talking about earlier in your presentation, I believe it was Mark asked, is there a name for the concept that measuring something alters the system?
Is there
a
name?
technical term for that?
I would just call it collapsing the wave function.
Mm-hmm.
It's probably the way.
Right.
Or,
Okay.
I mean, I might even just say observing or disturbing the system, even just sort of touching it is enough to change it.
Right.
Just looking at it, just asking a question, or in some cases, even a non-observation. Like if I have the gate on one of the two slits, if the photon goes through the other slit, the fact that there was no detection tells me that it went through the other one,
Right.
which makes it a different experiment than if the slit wasn't there, or rather if the detector wasn't there.
Okay. Christopher asks a good question. Can you talk a little bit about the latest developments in quantum computing?
This is great. So this actually starts to get into that third infinity, the infinitely complex.
Right.
So the idea here in quantum computing is I can generate entangled pairs of spins, like in that delayed choice experiment. And now what I can do is I can do computations where instead of having bits, like a bit can be either a 0 or a 1, and I have a bunch of bits side by side, so like 0 or 1, 0 or 1, 0 or 1. Instead, I have this thing called a qubit or a quantum bit, which can be in both states at the same time. And I can do something where I'm calculating in parallel, where it could be 0 and 1 at the same time. And it's sort of like I'm branching off into these parallel universes. I can do all these calculations at the same time and then come back. And this is the idea of quantum supremacy, this idea that I can beat anything. I can beat any classical computer with a quantum computer. I mean, so far, most of the quantum computers that have been built have been very small. I think I saw something like 10 or 20 qubits is the largest that they've gotten to, because these entangled pairs of spins are very hard to generate, because obviously you disturb them in the slightest way, they're no longer entangled in the same way. It's a little difficult to do, although some of the latest research now, I mean, a lot of the classical way of, I use classical kind of in a weird way, the classical way to do this is kind of an atomic physics way where you generate these particles, but it turns out there are even better ways to do it using materials, where you just have solid materials which just by the nature of the interaction of electrons tend to produce these entangled pairs of their own accord. In fact, some of the materials that I study are what are known as frustrated materials, where they're trying to order magnetically, they're trying to align, but there are interactions which prevent that from happening, that require them to be anti-parallel, but it doesn't allow them to settle down. And that could be used as a qubit. And these things can be stable at a variety of temperatures. You can also have lots and lots of them, right? You know, a little piece of material has 10 to the 23, you know, Avogadro's number of atoms. So if you could harness that, you could make an enormous quantum computer in a very small space. Now, of course, there are some consequences of that. Like our meeting right now is secure because there's a passcode and there's a Zoom ID. So even if some hacker someplace was going there and trying random IDs and random passwords, it would take a while for him to get in. Or if they were trying to hack into my bank account or getting past, you know, that little lock and key that you see on the web browser, that's because there's encryption, usually like 128 bits. So 128 zeros and ones. So to try to guess that, that's 2 to the 128 guesses you'd have to go through. And you could figure take 2 times 2, do that 128 times, your calculator will melt down before you get there. It takes a long time, but if you could do this with a quantum computer, you could break that sort of encryption very, very quickly. So that's going to be a problem.
Yeah. Is
for security. You know, the black hats and the white hats are always racing each other. And usually the black hats are ahead because they have the ability to strike first. So the white hats have to try to guess what the black hats are going to do next and to close up the loopholes as soon as they find them. But this is going to make it a lot more difficult to keep up with that.
Thank you.
Let's see.
Al had a question, and I think you already demonstrated this. Is there a way for us to do the slit experiment at home? Is
Yeah,
the
there's an
laser
easy
that
way
you
to
showed
do
us,
it.
was that a good example?
Yeah, so if you can get a diffraction grating, that's one way to do it. If you don't have a diffraction grating, you might be able to use a CD in order to do it. Because CDs
right.
have little lines on them.
Sure.
Let me see if I have one here. I think
Or
I don't.
DVD.
If you shine a little laser or something at a CD, you'll see that there'll be light at certain angles and not at others. Or if you have a diffraction grating, you can break up, or a prism. Well, a prism wouldn't show you diffraction. But yes, you can do something like that. Now, the double slit with one photon at a time, where it really gets interesting, that's harder to do because then you need a really, really sensitive detector that can pick up single photons. So normally what they use are what are called single photon avalanche detectors. But if you had a good astronomical CCD camera, you might be able to do it if you had a really, really dark enclosure. If you have a light, you cut it, get a bunch of like moon filters. I don't know how many you'd need. you could calculate the number. If you know how much power is going into the laser and you know how much energy is in one photon, you put enough moon filters that you're getting one photon at a time. You shine that at your little slit. You have a CCD on the other side, big dark enclosure. You have to cut out all of the light. You could, in principle, do it. It would be pretty difficult, but I would say like an advanced undergraduate optics lab at most colleges would be able to do this. You know, you're talking $1,000 to a few $1,000s investment because you're measuring single photons at a time. That's what makes it difficult.
Okay. We have a question about Hawking radiation. You know, black holes at the end of the universe, how long would it take for the remaining black holes to lose all their mass through Hawking radiation?
Don't quote me on any numbers. The interesting thing about Hawking radiation is that it is inversely exponentially proportional to the mass. Massive black holes radiate very, 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 very slowly. And in fact, they gain mass at orders of magnitude higher rates. So you would have to wait a tremendously long time till like there's nothing left except the black hole. And then you would start to see the Hawking radiation. But then as the black hole gets smaller and smaller, the rate of radiation gets bigger and bigger until eventually it gets down to a really small size. And then it just kind of poofs away suddenly. I mean, I could tell you I'm not planning to be around for when that happens. So it's a very long time. It's like 10 to some ungodly number of years.
Yeah. It's a long way away. Okay. Another question from Jeff. Can you explain why fusion stops with the creation of iron inside a star at the end?
Ooh, that's a really good question. All right, so here's the idea. Maybe I don't know if I have a whiteboard here. No, I don't. All right. Maybe I can bring up paint and I will draw a little picture. Let's do this. Oops. So here's what happens. I'm going to draw a little graph. Let's pull out my tablet here. Let's say that I had I'm going to have to move to another screen. Let's say I've got some like rolling hills or something here, like something like that. And let's say there's a ball sitting here. The ball naturally is going to go in that direction, so it's going to try to minimize its energy. That's what systems tend to do. They try to minimize their energy. Now, a little bit more practical. What if I had a ball over
here? Seeing anything here?
You're drawing something, we don't see it.
Because I moved it to another screen. Okay.
Yeah, we're on a different screen.
Resume that. Okay. Yeah, so I started with a ball over here. It's going to tend to roll down the hill. Now, if I put the ball over here, it's perfectly happy to stay there unless I kind of kick it. Right? If I kick it up to this point, it's going to go, oh, look at that. I can go down that way. And then I reach an even better minimum down here. And that's the concept of activation energy. So, right, the way I'm doing this is it's physical space, right? This is like position, and this is energy over here. But this doesn't have to be position. This could be something else. It could be like chemical composition. So here's a good example. You put gasoline inside your car. That's where gasoline is. You mix that with oxygen, you provide a spark. That's the activation energy that gets you up here. And then, oh, look at this. I can go this way, and that produces CO2 plus H2O, which is even lower energy. And of course, there's an energy difference, and that's what makes your car go. That's how your engine works. That's how chemical reactions work. Well, nuclear reactions work sort of the same way. Let's make a slightly bigger picture, starting from something like hydrogen, which is over here. I can combine hydrogen atoms together and I can make them into helium. And there's a tremendous amount of energy that comes out of that. And that's what the sun is doing right now. Now I could take helium and I can combine that and make maybe carbon and oxygen out of that. There's even a little bit more energy. And then maybe I can combine that a little bit more. And then I get to, what is it, silicon, I think is the next up in that list. And then eventually I get to iron out here. Now the problem is if I try to go beyond iron, the hill starts going back up again. So in fact, the minimum is somewhere around iron or nickel, depending on exactly how you compute it. You start going up the hill again, which means you have to put energy in. Now, of course, I could start at the other side with something like uranium. And now if I take uranium and I break it down, I get energy out of that. And that's how nuclear reactors work. We call that fission because we're breaking it apart. And if we go this way, we call it fusion. And it turns out that iron is at the bottom. All right, so that answers the question without answering it. You might ask, why is iron at the bottom? And there's some interesting subatomic physics here. And it essentially has to do with the nucleus. So let's draw a nucleus. This is kind of a long answer. I don't know if I want to, if you guys are interested in hearing it, I can give you the long answer.
Go for it.
Yeah, sure.
All right. So inside a nucleus, there's basically two forces that we're concerned with. There's the strong force, which attracts all of these all these nucleons together. It's like glue. Very, very short range, but very, very strong. So it is like glue, right? Glue does nothing if the two particles are separated, but if I stick them together, good luck getting them apart. I'm remembering those old commercials with the guy with the helmet and he stuck himself onto the I-beam and he was hanging from it. Am I dating myself here? Was it super poly grip or something like that?
Poly grip or crazy glue.
Yeah, we put it on the helmet and he's hanging off there.
Yeah.
That was crazy glue. Yep.
Oh, it's crazy glue. Okay.
Polygrip.
So anyway, the strong force is like glue, but it's very short range. Now, on the other hand, you have the electromagnetic force. Well, some of these particles are neutrons and electromagnetism doesn't care about that, but some of these are protons, and those protons are going to repel. Now, the electromagnetic force is about 100 times weaker, so all else being equal, the strong force wins. The problem is electromagnetism is long range, unlike the strong force. So as a nucleus gets bigger, these ones that I'm adding on the outside experience the electromagnetic repulsion, but they're not strongly attracted to the others. So generally, as I get to bigger and bigger nuclei, at first you're gaining because you're getting more of those attractive forces. So that's why you're going down in energy as you're building up the nuclei. But eventually you start getting so big that now that electromagnetic repulsion starts to win and you start going back up. And now just because of the ratios of the strengths of these two, the minimum is right around iron. Now, if you made the strong force a little bit stronger, then maybe the minimum would be a little bit further out. If the strong force was weaker, then the minimum would be over here someplace. We live in a universe that happens to have iron at the minimum. And then there's probably a really long answer, which goes into what if the universe was different and it wasn't iron where it ends. That could be a whole talk in and of itself.
Right.
And so the creation of the heavier metals, or the heavy elements, requires a lot more energy to be put into the system.
Yeah, it still happens inside stars, but it becomes parasitic. It's something that's robbing energy.
Right.
You can produce the heavier elements inside stars, but it steals energy essentially. And you can get up to like the middle of the periodic table doing that. The really heavy elements, the only way to get those is either supernovas or neutron star mergers, where now you just have a whole bunch of stuff happening all at once, and that's where you can get the really heavy elements. So things like gold and lead and uranium, most of those are coming from these supernovas or neutron star mergers.
Okay.
And these absorb a lot of energy making that, but you have tons of energy available.
Okay, thank you.
Yeah, I'm good at long answers. So Mark says, do you mean stars in the end of their life? I'm not sure what that was in relation.
That was in reference to the last question about iron.
Oh, okay. Yeah, so yeah, as stars get older, they produce heavier and heavier elements. They in fact, like in the really old stars, things like Betelgeuse, it's almost like an onion, right? Where you're like burning silicon into iron in the center and then carbon and oxygen into silicon. Then eventually there's a hydrogen burning layer outside that. But yeah, when you reach iron, that's the end of the line. You stop producing energy, and that's when the star collapses on itself.
Cool.
You see a question here. If everything is made of quantum, how is space-time explained? That's kind of a hard question because we think of space-time in, sort of in the framework of general relativity, where it's sort of this stretchy thing like a trampoline where you put the bowling ball on it and it stretches space-time. We normally think of it that way. But it certainly has a different meaning in quantum mechanics because everything is kind of fuzzy, right? Measuring positions, measuring velocities, measuring energies. It's all fuzzy because of the uncertainty principle. Yeah. The particle being in two places at one time. Feynman said he obtained a score of only 125 on an IQ test. Yeah, I guess that's one of the reasons why they don't use IQ tests anymore.
Okay, well, thank you, Jeremy. This is really a fascinating topic, and so thank you for your time explaining all this to us. And so thanks for being here. And so I'm going to close out this part of our presentation for our members. Please do stick around. We do have a little bit more to discuss. We'll have a business meeting and that sort of thing. And so for those of you joining us on YouTube or here on Zoom, we want to thank you for being here. So thanks. Our next meeting is going to be in March. And Mary Lou, could you remind us what the speaker is for the next program?
No, it's March 10th,
Right.
and it's Eric Jensen, and he's going to talk about exoplanets and planetary systems that have multiple planets and why they are somehow tilted in their orbits relative to each other. How does that happen? How does a disk get tilted?
Right. Great. Very cool. Okay.
Very nice, Jeremy. Thank you very much.
Yes, thank you very